Just take a look around you for a second. I bet you can spot, half a dozen plastic things without even trying. But have you ever stopped to wonder how that one material can be used for something rock solid, but also something paper thin? Well, it's a pretty cool story that blends chemistry and engineering, and that's exactly what we're going to break down. So this is the big question, right? How can your hard, super protective phone case and a flimsy plastic grocery bag both be made from the same family of materials? The answer? Well, it's like a secret personality change that all plastics can go through, and the key to unlocking it is temperature. All right, to get to the bottom of our phone case mystery, we've got to understand a plastic's two secret personalities. And it all boils down to one single critical scientific idea that decides whether it's going to be stiff or bendy. And here it is, the hero of our story, the glass transition temperature, or TG for short. Now, this is not a melting point. Don't think of it that way. It's more like a personality switch. Below its TG, a plastic is hard, brittle, kind of like glass. But you heat it up just past that temperature and boom, it becomes soft and rubbery. This one number, this is the key to everything. So what's actually going on at a microscopic level? Well, below that TG, the long polymer chains that make up the plastic are all locked up, frozen in place, totally rigid. Think of a box of uncooked spaghetti, stiff, brittle. But once you heat that plastic above its TG, those chains get just enough energy to start wiggling and moving around. They're not flowing like a liquid, it's more like a bowl of cooked spaghetti. They can slide past each other, and that's what gives the material its flexibility. Okay, so this is where things get really, really clever. Scientists and engineers, they don't just find out a plastic's TG, they actually control it. They can literally design a plastic's properties by tweaking its fundamental chemistry. So let's take a look at the control knobs they have at their disposal. And these are the main levers they can pull. They can mess with crystallinity, that's just how neatly those polymer chains are able to pack together. They can change the molecular mass, which is basically the length of the chains. They can add big, bulky side chains that kind of get in the way and stop things from moving. Or they can add plasticizers, which are these little molecules that act like a lubricant, helping everything slide around more easily. Even the 3D arrangement of the atoms, what's called its stereoregularity, plays a part. Every single one is a knob they can dial in to get the exact TG they want. And here you can see exactly how that plays out. So you want a high TG for a really rigid, strong material? Okay, then you're going to design a polymer with highly organized crystalline chains and a really high molecular mass. But what if you need a low TG for something super flexible? Then you'll want a more jumbled up, amorphous structure, and you might toss in some plasticizers to help those chains move around, even at room temperature. It's cause and effect. Theory is one thing, but let's make this real. We're going to look at one of the most common plastics on the entire planet to see how this engineering takes the exact same starting chemical and creates two totally different materials. So meet polyethylene, or polythene. It's incredibly simple, super cheap to produce, and I guarantee you've interacted with it multiple times today already. It's just made by linking together these simple little ethylene molecules. But how you link them changes everything. And this table just lays it all out perfectly. On the left, you've got LDPE. That's made with crazy high heat and pressure, and what you get is that flexible, waxy material, used for stuff like grocery bags. Now, on the right, HDPE. You change the recipe, way lower temperatures, add some specific catalysts, and you get a totally different beast. A strong, stable material used for things like construction parts and car bumpers. Same ingredient, two completely different plastics, all by controlling the final structure. And here's a fascinating little real-world detail that connects right to this. In an effort to cut down on waste, as of late 2022, the Indian government made it a rule that plastic carry bags have to be at least 120 microns thick. The idea is to make them more durable so people will reuse them, a direct policy decision based entirely on the physical properties of the plastic. Okay, so we've cracked the chemistry that gives a plastic its personality. But how do we go from these raw polymer pellets to the actual objects we use every single day? Well, that's the final piece of the puzzle, the amazing science of molding. And yeah, there is not just one way to shape plastic. As you can see, there's a whole toolbox of different techniques, and each one is perfect for a different kind of job. We're going to zoom in on two of the most common ones, injection and compression molding. First up, injection molding. This is the absolute workhorse of the industry. It's mainly used for thermoplastics. The plastics that you can melt down and reform over and over again. We're talking about things like Lego bricks, bottle caps, the casing on your computer mouse, that kind of stuff. The process is basically this insane rapid-fire cycle. Plastic granules get melted down, then they're injected with incredible force into a super precise steel mold. It cools down just long enough to turn solid, and then pop, out comes a finished part. This whole thing can take just a few seconds, which is how they can mass produce millions of identical items so quickly. All right, now for a totally different way of thinking, let's look at compression molding. This method is usually for thermosetting plastics. That's the kind that goes through a chemical change when you heat it, a change that's permanent. You can't remelt these. So here, the process is different. You start by putting plastic powder into a heated mold. Then you apply a ton of pressure. That combination of heat and pressure doesn't just melt it, it actually triggers an irreversible chemical reaction called cross-linking. This is where all those polymer chains lock together forever, creating this super strong heat-resistant structure that you need for things like electrical insulators or the handle on a cooking pot. So let's zoom back out. We've gone on this whole journey, right? From the invisible world of wiggling polymer chains all the way up to these massive industrial machines that are literally shaping the world all around us. This quote really just says it all. The absolute genius of plastic is this incredible balancing act. It has to be strong enough to actually be useful, but at the same time, it has to be flexible enough to be shaped into almost anything we can think of. It's a huge engineering challenge that's been solved, and solved brilliantly. So, the next time you pick up your phone case or a plastic bottle, maybe you'll see it a little differently. It's not just a piece of stuff, it's a little masterpiece of controlled chemistry. And it kind of makes you wonder, doesn't it? What other invisible engineering is hiding in plain sight all around us?